Hello everyone, my name is Donghyun-seo. I am a PhD student in Electrical and Computer Engineering at Purdue University. Today, I will be presenting the paper Patterned Ground Co-planar Capacitive Asymmetry Sensing for Millimeter Range EM Side Channel Attack Probe Detection. Here is the outline of the presentation. I will provide the introduction, background information, and explain why we need approaching probe detection. And then I will propose the patterned ground coplanar capacitive asymmetry sensing and system. Then we'll show the simulation result. Side channel analysis based attacks can be implemented on a mathematically secure physical platform, which leak critical information through power dissipation, electromagnetic radiation, timing of the encryption operations, cache hit and miss, and so forth, allowing an attacker to extract the secret key from the device. In order to protect against EM side channel analysis attacks, various countermeasures have been proposed such as logical, architectural in design specific, and circuit level. However, these countermeasures require significant overhead in terms of power and area. To solve the problem, this work adopts a proactive strategy to detect the presence of an EM side channel attacker even before an attack is mounted, thereby alleviating the overhead incurred by a countermeasure against such attacks. Also, this strategy of EM side channel analysis attack detection can be augmented with an existing countermeasure such that the protection circuitry is only enabled when an attack is detected. This would significantly minimize the power overhead compared to the always-on countermeasure. Until now, we looked through why we need approaching probe detection. Here is the previous related work in EM side channel analysis attack detection. This figure describes the previous work on the attack detection technique. This employs an inductive sensor coil-based LC oscillator. It detects variation in the EM field caused by an approaching EM probe. When an EM probe approaches, the inductive sensor, the mutual inductance between the EM probe and the integrated sensor coil, increases. As current flows through the inductive sensor coil, the oscillation frequency of LC oscillator shifts due to the changing mutual inductance. When an EM probe approaches, mutual inductance changes, and consequently, the oscillation frequency of the LC oscillator shifts. Thus, it is possible to detect the presence of an EM probe by detecting the frequency shift using an LC oscillator. However, the effective detection range between the EM probe and the sensor coil is limited to a maximum of 0.1 mm. In order to resolve the issue, we proposed advanced sensing structure which is called patterned ground coplanar capacitive asymmetry sensing. This consists of 4 metal plates and patterned ground grid. The metal ground grid is formed using the metal layer immediately below the plates. Although different metal layers are used coupling plates, they are close enough to form capacitance. It senses the interplate and plate ground capacitance. As an EM probe approaches, the symmetry of the 4 metal system breaks and the capacitance between the pair diverges from the baseline capacitance in different amount each. The goal of this work is to enhance the detection range of an approaching EM probe and to reduce power consumption by operating the circuit intermittently at under 1% duty cycle. Now, let me explain the patterned ground coplanar capacitive asymmetry sensing structure. Plate-to-plate and plate-to-ground capacitances will depend on the presence of object between the plates and the surrounding environment, as the electric field lines between the plate would get coupled to any nearby object. Coplanar plates and patterned ground that are not affected by the surrounding environment form their own capacitances. If an EM probe approaches a pair of metal plates, some of the electric field lines between the plates and ground will get coupled to the probes, and thereby affecting the interplate capacitance and hence the peak resonant frequency of the corresponding LC oscillator system. This resonant peak frequency of the LC oscillator can be tracked to detect the presence of an approaching probe. Let's talk about patterned ground more. In CMOS integrated circuit technology, the ground grid always exists, and any metal plates and the ground grid would form a capacitance. If the ground metal covers the whole metal plate area, strong electric field lines are formed. Since these field lines are not affected as much by an approaching probe in the surrounding environment, it would lead to degradation in sensitivity. This ground patterning improves the sensitivity by lowering the absolute capacitance between the plates and ground, while raising the relative change in plate to ground capacitance when a probe approaches. Until now, we observed the operating principle of patterned ground coplanar capacitive asymmetry sensing. Now, I will talk about the detection system level. This figure describes a system diagram and detailed circuit schematic of the EM side channel analysis attack detection. It consists of two LC oscillators, mixers, low-pass filter, resistive feedback amplifier, and the digital divider. Two LC oscillators are connected to patterned ground coplanar capacitive asymmetry sensing plates. The resonance peak frequency of the LC oscillator depends on the value of the effective interplate capacitance, here C tank. The C tank consists of three different combinations of capacitance. The first is the capacitance formed between the plates, here C co, and the second and third is the capacitance formed between the plate and patterned ground, here C1G and C2G respectively. The capacitance value of C1G and C2G are the same because the size and dimension of metal plates are equal and the patterned ground is symmetrical. As an EM probe approaches one of the patterned ground coplanar capacitive asymmetry plates, the two LC oscillators produce a difference in frequency depending on the asymmetry in capacitance. To amplify difference between two LC oscillators, the mixer that performs frequency translation by multiplying two oscillation frequencies, low-pass filter, resistive feedback amplifier, and digital divider are used. By downconverting the sensing frequency, the frequency shift change rate is increased, leading improvement in detection range. Now, let's analyze the simulation result. Here is the simulation result of sensitivity and maximum detection range of patterned ground coplanar capacitive asymmetry sensing plate. This result shows the simulated capacitance value of patterned ground coplanar capacitive asymmetry sensing as the EM probe approaches the sensing plate. In the absence of the EM probe, the effective interplate capacitance, C tank, is measured to be 8.54 femtofarad. When the EM probe approaches, C tank reduces due to the coupling effect of the EM probe. As the distance between the sensing plate and the EM probe becomes under 0.01 mm, a C tank changes of over 40% is observed, while at the distance of 1 mm or lesser, the capacitance diverges by over 8% compared to the baseline. From the simulation result, the difference in the seed tank capacitance changes can detect an approaching attacker. Here is the simulation result of EM side channel analysis attack detection circuit and systems. This graph shows the simulated oscillation frequency change rate before down conversion. As the distance between the sensing plate and the EM probe becomes under 0.01 mm, an oscillation frequency changes of over 8% is observed compared to the baseline. The right graph shows the simulated output frequency of the whole system. In the absence of the EM probe, the output frequency is 253 MHz. As the distance between the sensing plate and the EM probe becomes under 10 micrometer, the output frequency changes of over 238% is observed compared to the baseline frequency. These results demonstrate that the patterned ground co-planar capacitive asymmetry sensing structure can detect an approaching attacker, leading improvement in sensitivity and detection range. Here is the conclusion and performance summary. The results demonstrate that patterned ground co-planar capacitive asymmetry sensing detection can be successfully utilized to sense approaching EM probe for a probe chip distance of under 10 micrometer with over 40% deviation from the baseline interplate and plate ground capacitance. By down-converting sensing frequency, over 238% improved for baseline frequency signal. This provides a 10 times improvement of detection range over 100 micrometer of inductive sensing as shown in table. This intermittent sensor operation consumes 7.5 microwatt of power, which is much lower, like 2 times more compared to the previous work. Hence, using the proposed patterned ground coplanar capacitive asymmetry sensing detection intermittently, an EM side channel attack can be proactively detected, and consequently, any countermeasures can be turned on, reducing the power overhead significantly. I've presented the paper Patterned Ground Coplanar Capacitive Asymmetry Sensing for millimeter range EM side channel attack probe detection. If you have any question, feel free to ask. Thank you.